All right. Hello, everyone, and welcome. Good morning, good afternoon, and good evening, depending upon what part of the world you're in. Thank you so much for joining us at this inaugural Metaverse Creators Hackathon here in December of 2022. For those of you who don't know me, my name is Scott. I am the co-founder and CEO of a technology startup called Dimension X. My co-founders and I formed this Metaverse Creators community as a way to try and create a universal platform agnostic center for all of us to be able to get together, learn, grow, network, and showcase. In that spirit, we have with us today Turbo Makes Games, also known as Johnny. He is one of, if not the number one voice in the social media world regarding the data-oriented technology stack, a high-performance subset of C# that has some special magic about it that is part of the Unity game engine. So again, I just want to thank everybody for joining us. I know it's late in certain parts of the world. Other people have school. I'm so stoked to see everyone here today. And so with this, I would like to start off with some housekeeping, some ground rules. With this hackathon, it is a 24-hour sprint, the goal of which is we're going to provide you with some template code, some template projects that are going to have in it some assets and some code that you are free to use, extend, demolish as you see fit. We are also very encouraging for you to go ahead and use any openly available free open source type assets or to make anything you want from this point going forward. We do ask, just for the sake of fairness, that you avoid using anything paid or licensed that other people might not be able to take advantage of, or any assets that you have sitting in your library that you've worked on over the years. It is an honor system, but we are trying to keep this as fair of a friendly competition as we can. With that said, you will be able to find more of the actual rules in the Discord forum that we created. So we encourage you to go ahead and take a look at that and ask us any questions if you have any. Now, to get into the details, the meat and potatoes, as it were, dots. Why? Why is this hackathon about dots? Well, there's a lot of reasons for that, but I want to make sure that you get the best answer possible. So to explain a little bit more about what dots is and why it's important for a community like Metaverse Creators, I'm going to go ahead and hand over the mic now to Johnny. Thank you, Johnny.
Awesome. Thank you so much, Scott. Definitely looking forward to participating in this hackathon. Again, it is centered around Unity's data-oriented technology stack, which, if none of you are familiar yet with, data-oriented programming, it's kind of a different way of programming than object-oriented programming. One of the reasons that I'm really gravitated towards data-oriented programming is because, the way we structure our code and everything, it's much more similar to how the computer naturally stores and processes data. And so I really hope that, as you start going along with, using this data oriented technology stack, that you really kind of find some of the value and things that you can do and really, optimize your code to, not only get really high performance, but be able to, just kind of separate the data from the logic, which is going to just kind of, make your code a lot more modular. So that is something that I definitely want to encourage you all to do during this hackathon. As you're going along, definitely try a bunch of things out. I'm sure, I know a lot of you have kind of varying levels of experience with Unity's data-oriented technology stack. Many of you, this is going to be your very first experience. So, definitely, welcome in, and I hope you have fun with it. So yeah, really just try and push yourself to do as many different things as you can with it. Try different implementations. If something isn't working out, try a different way of approaching the problem. That's kind of one of the things that I find, really beneficial with Unity's data or technology stack is just, that separation of the data from the logic. It really allows us to test out different implementations of things, especially during the prototyping phase really easily. So, definitely encourage you to, really just have fun with this. Again, try many things out. And yeah, definitely looking forward to participating in this event here.
Awesome. Thank you so much, Johnny. So to reiterate, what we are going to be handing off here in just a few minutes is a set of templates, one for 2D and one for 3D. What we did to make this as easy as possible for all skill levels is we actually went ahead and grabbed two of Unity's own sample projects. You might be familiar with them. One is the microcart sample. The other is the microplatformer sample. And we went ahead and extended them with some basic DOTS code to try and give you guys a jump start on how to go about integrating DOTS code with standard mono behavior or game object workflows. So I'm about to release that in just a second here. And before I do, though, I want to go ahead and clarify that we don't expect you to just jump in there and figure it out. So once I release this template, you have one of two options. You can either sign off from here, take the template, join your team, and just start cranking. Or if you want more of a walkthrough, you can stay put. You can stay on this channel here, and we're actually going to walk through each of the projects, Johnny and I together, and explain what each of the DOTS scripts are doing and how to go ahead and work through them. Okay. So with that said, I'm now going to start sharing my screen. And I want to give everybody as fair a chance as possible here. So we're going to do this together. Okay. So here I am on the Metaverse Creators Discord. If you scroll down to the bottom, you'll see the DOTS Hackathon 2022 forum channel. I'm on the Day of Expectations pinned post. You can see here, here's the zip file. Okay. So count it down with me, guys. I'm going to count it down from 5. The second we hit 0, I'm pressing enter and it's going live. So here we go. 5, 4, 3, 2, 1. They are uploaded. You are now live. Hackathon is live. Thank you so much for attending. Good luck. And so now let's go ahead and open these up and explain what's inside. So for this first one, we have the microcart demo. All right. So first things first, when you first launch the product or the project, you're going to be greeted with these 4 folders. Both microplatformer and microcart are organized the exact same way. I kept them sequential for ease of access and organization. So on the far left, you have 000. That's the template files. It's the original product template files, right? So everything that's in there is just the raw original Unity sample project. So if I go into here and go to carting, scenes, these are your main scenes. If I click main, it's going to load everything up. And here you have everything you need for a very basic mobile-friendly microcart game. Okay, so I can press play here. And it's got most of the work already done for you. So we've got audio, we've got animations, we've got GUI. You can play through the little circles here. They disappear and count towards your objective. Right? We've even got a pause menu. And then I finish and it moves on to the next screen. Okay. So that's already good to go in there. You can extend that, mess with it, play around with it all day. You have all the prefabs, all of that. So then what we did was we went ahead and took that same exact scene, right? So we're going into the DOTS primer 001, 000 scenes. And then you've got this DOTS example.unity scene. And you'll notice nothing changed except for these 2 guys right here. All right, so this is very important. What we're trying to showcase with this hackathon is that DOTS is not an all or nothing thing. Right? That was something I got as a reaction quite a bit from my summit talk when I went through DOTS, was people would say, oh, I don't know if I can convert my entire project to DOTS. That seems like a really heavy lift. Right? So one of the points of this hackathon is to show how you can take a pre-existing project that is using traditional game object workflows and you can integrate DOTS technology into it. Right. So for the microcart, we've got the procedural way of doing this. That's very mono behavior heavy. However, if you come over here to this DOTS baking scene, this is using what's called a sub scene. I'll let Johnny explain that here in a minute. And so we provided you also basic examples of both. Okay. So what I want to explain here is entity spawner is if you need to really get into the underbelly, if you will, of how to generate your entities. You're doing them entirely procedurally, building them up from scratch, right? And then with the baking methodology, you're grabbing more of the prefabs and converting those. Okay. So Johnny, actually, if you would like, can you go ahead and explain to us what this baking workflow looks like?
Yeah, totally. And so I think, if the people who have experience with Unity already, they may already feel a little bit more comfortable with this particular baking workflow. Again, you'll see that Scott mentioned that we are using essentially a sub scene here. You'll see that the scene is the sub scene rather is called entity spawner. Now that basically just is sitting as a regular, asset in the hierarchy there. Now, everything, any game object or anything that we put under that particular subscene, that's essentially going to go through a baking process, which is basically you can think of it as it converts a game object into an entity representation when we actually go ahead and run the application. Now, you'll see that if we take a look at that spawner mono right there, which is currently a game object under that subscene because we're not in play mode right now. You'll see that over in the inspector we have sort of a very familiar interface. Again, if you're familiar with Unity, where we have just kind of the regular transform on that, as well as a spawner mono script, which is a script that I had created there. You'll see that there's just kind of like a number of fields, basically, different types of parameters that we're modifying about, how many of these prefabs that we want to spawn and kind of some, range of where we want it positioned in the world and all that. And you'll see that we do have a entity prefab, which is basically just a prefab field called entity right there. There's really no difference between that and any regular prefab. You'll see, if Scott goes ahead and just clicks on that entity prefab right there, again, very similar thing. We have, just the basic, transform and mesh render. It's basically just a sphere there. And then so now I guess we can just go ahead and give a little bit of a demonstration of it about, what happens when you enter play mode here. So you see that basically, we've created this scene where it just spawns a bunch of these spheres into the world, and then all these spheres are basically going to be attracted to the player's cube. And then, as Scott moves around, you'll see that all the spheres, follow the player at their new position right there. And so basically, you'll see that if you look over in the hierarchy, it doesn't really look like anything has changed. You're not going to be seeing anything different. Now, there is actually a way that you can, say, inspect all of the entities that are inside the scene. Where, yep, if you just go up to Window and then down to Entities, and then there's the hierarchy. So right now, Unity has it basically kind of separated out where there's two different hierarchies. So there's just kind of like the regular hierarchy, which you are all familiar with, and then there's the entities hierarchy. Now, actually, you're going to have to press that. You see the little orange button? Actually, yeah, if you just go ahead and back into, yeah, you can go ahead and dock that there. And then, yeah, we can kind of have a side by side. And then, so yeah, once you get back into play mode, you'll see, well, yeah, now you can go ahead and actually see all the entities basically there. And if you want, you can actually go ahead and select any of those entities. And then you'll see that over in the inspector, it looks a little bit different now. So this is kind of the entity version of the inspector, where you can see all the data components. Now, the data components are going to be a little bit different than just kind of the traditional Unity, components of them. So, if you remember on the prefab, we just had, a normal Unity translation. Or a normal Unity transform right there. Yep, just like that. And then when we go actually inspect the entity version, if you go back to, just one of the entities, you'll see that now there's actually a couple of different components that amount to what is basically the translation component. So you have your world transform, local to world. You don't really need to worry about, all the specifics of each of these. If you are going to be modifying the position of something, the local transform is most likely going to be the one that you're going to be modifying there. But you can just kind of see that there is a little bit of a difference when you actually go ahead and run your application, that the entity kind of goes through this baking process, which basically creates a new entity, and then it's going to go ahead and add all these data components to them. Now, data components are a very important concept because this is kind of the core of data-oriented programming. Everything is centered around the data, so we create all these data components that actually store, again, things like the position of where the particular entity is in the world. And we can also have things on that. So you'll see that we have this. There's this C speed component. So that speed component basically controls how fast any given entity moves. And so if, Scott were to select any number of the different entities, you'll see that we've randomized this speed value. So it's, again, this is kind of unique per each entity. So that's kind of the basics of, what entities are, and kind of they have these components associated with them. Now to actually speak about, what is actually causing these entities to move, that is where systems come into play. And so yeah, there's kind of a couple of different ways that we've gone ahead and created these systems. Or actually, should we talk about the baking more, or do you think that it makes sense to kind of go into systems? Where should we start with
Yeah.
the code here?
So we can start with the baking system if you don't mind, just to kind of go through how we're converting over
Yeah,
from
just kind of
mono.
finish off that thought. Yeah.
Exactly. Yep.
Yeah, so I've used kind of the baking workflow here, where we basically have that kind of spawner sitting in the sub scene, and you'll remember that I have that spawner mono, which was that custom mono behavior script. You'll see it's a very simple mono behavior script. It doesn't have any methods or anything on like that. It's all just public fields. Now, it is important that these all need to be public fields, because when we get into the baking step, which is next, we do have to actually access those public fields. So again, yeah, those are just all the fields that we're setting within the editor. Now you'll see that we do have this spawner baker, and you'll see that this is basically a class that inherits from this baker. And you'll see that inside the little type brackets there, we have spawner mono to basically associate that baker with that mono behavior that we had created. Now you'll see that it'll force you to create a public override for the bake method here. And you'll see that bake method takes in a type of spawner mono, just called authoring. And then that is basically a reference to the mono behavior on a given entity. Now, basically what this baking process does is it just takes all those, well, we kind of tell it what to do inside the baking process. So in here, basically what I'm doing is I have one data component here that basically keeps track of all the data associated with spawning entities into our world. And you'll see that that data component is called C spawn data. Actually, it might be helpful if you go into that just so people can see what that looks like there. So yeah, you'll see that it again is a fairly simple thing here, because these data components, they literally just have data on them. It's typically not best practice, even though it is a struct. It's typically not best practice to include any methods on these data components. Again, the main purpose behind these is to just hold data. Um, and again, you'll see. So yeah, it's a public struct, which is going to implement the I component data interface. And then you'll see that basically we have all these fields here, and these fields are basically all going to be associated with how we want to spawn entities in our world. So you'll see at the top, we have a public entity type for our entity prefab. And then after that, we again just have just kind of generic things about, how many we want to spawn, what's kind of the minimum and maximum spawn position, what is the scale, and minimum and maximum speed. So we can kind of randomize things a little bit there.
Johnny, would you mind explaining a little bit why there's a float 3 here instead of a vector 3?
Great point. Yeah. So with with these data components, one thing that we do need to keep in mind is they all need to be of blittable data types. So we can't have any, managed types. So you see that we don't have any like game objects or transforms. We can't have any animators or anything like that. So they all basically need to be of special type here. And the reason for that is because when we want to use these data components in conjunction with the burst compiler, which is one of the ways that we can get really massive performance gains, is that we can only use these unmanaged blittable data types. Now you'll see that as Scott pointed out, we're using a float 3 rather than a vector 3 for position. Again, if you're familiar with Unity, you may have used the vector 3 type to control where a position of something is. So the float 3 actually comes from the Unity mathematics library. And I should point out that I don't think there's anything really stopping you from using a vector 3 in there. because it's basically just kind of a simple type, again, just comprised of a couple of floats. However, the float3 type comes from the Unity mathematics library, which is integrates really nicely with the Burst compiler, and it basically allows us to do a bunch of kind of optimizations on the back end that are going to really optimize for performance. So we're using the float3 type rather than the vector3. So good to call out there.
Awesome. Then if we go back into the spawn entity system, so this
Actually,
baking.
we'll go back to the baking system real quick just to kind of finish that out, and then we can show what the spawning looks like.
Yeah, did I
It's on
click
the
on the wrong
spawner
one?
mono.
Spawner mono, thank you. Yep. Go ahead.
So yeah, you'll see here inside the baking, what we're doing is we're basically just calling that add component method, and in there we're passing in a new data component. You'll see that here we're creating a new C spawn data. And again, we're just going to go ahead and populate all the fields with things from our authoring component. So for example, the number to spawn, all we do is just do authoring dot number to spawn. Again, that kind of goes back to just having everything as public values there. You notice for the entity prefab, we do have to do something a little bit interesting where we do a get entity, and then we pass in authoring.entity prefab. Now, the reason for that is because if we actually go back up to the mono behavior, you'll see that we define the entity prefab as a game object. So again, we're just basically dragging in a regular game object prefab, and then during this baking process, it's essentially going to get converted to that entity representation of it. And basically, yeah, that get entity method is going to essentially convert that game object into an entity and store it in our entity prefab field there. And then, the last thing that I'm doing here is creating a new C spawner random. And yeah, if you just want to pop open that data component real quick, you'll see that, again, it's just a very simple data component. This is using a public random value. And I should point out that this is using the unity.mathematics version of the random. So again, it's basically going to be fully compatible with the Burst compiler and everything like that. So then, yeah, if you go back to the spawner mono, then you'll see here, basically that's where I'm essentially creating a random seed for that random data component. So basically the kind of the common convention you'll see with data components is if you just have one field in a data component, you can call the variable in their value, and then it just kind of makes sense where you can say, I have data component dot value, because you'll have like the name for the data component. So it kind of is a common convention there. So you'll see that what I'm doing is I'm just setting value equal to random dot create from index, and then again I have a random seed, which is an unsigned integer there.
Okay, so just to recap with this workflow, what we are doing is we are taking a regular game object that contains your traditional mesh filter, mesh renderer, material. You'll notice there's no colliders. We'll get into that here in a minute. But strictly just a basic game object. This could even potentially have children game object or game objects. And then what that does is it goes into this spawner mono script that lives on a regular game object inside of a subscene. To create a subscene, you simply right click, new subscene, empty scene, right?
Yep.
And that'll create a new one of these that you can name whatever you want. And then you can stack things inside. Now, the way you know it's a subscene and not a regular scene is if I go into my scenes here, if I drag one of these in here, you'll see how this scene and this scene are on the same identical indentation, right? However, this subscene is not. It's indented in as part of the test baking scene. So that's how you know it's a subscene. The other way you'll know it's a subscene is you'll have this checkbox on it. If I unload this really quick, remove scene. Okay, so
it's kind of getting cut off in the entities hierarchy, but it has it in the regular hierarchy.
Oh yeah, it would help if I'm using the right hierarchy. There we go.
It
Okay,
is
so now
feature
I can come
execution.
here and I've got this little checkbox that I can turn off and on, right? If you don't have that checked and you press play, if I remember correctly, it will not parse it. Oh, it does.
So yeah, it still
Sweet.
should load. Basically, when you check mark that, that essentially opens the subscene, and that allows you to edit things inside that subscene.
There we go. All right. So all of that is the baking workflow. Anything else you'd like to cover on that, Johnny, before we actually, there is one more thing we need to cover, isn't there? And that is the actual system itself.
Yeah.
Okay. So this is the mono behavior piece. This goes on your game object. This is your baker that attaches to that mono behavior and creates an entity with these components. So the end result of this bake is an entity with a cspawn data and a cspawner random components on it, right? Two
And
pieces of data.
actually, we could probably go back and enter play mode and
Mm-hmm.
actually just have it spawn like one entity so your hierarchy doesn't get all gummed up with a
Sure.
bunch of stuff. But it might be good to just kind of show off what the entity representation of the spawner entity looks like.
Yeah. All right. So I'll need to get back into, actually, I should have done this smarter. I'm going to reopen my
So
entities
actually,
hierarchy.
if you have it selected in the regular hierarchy, you can kind of convert the inspector over.
Oh, can I? Okay.
Yeah, there's actually kind of a little bit of a glitch, I think. So you might have to like click onto another game object, like click on the player or something, and then back to the spawner mono. And then over in the inspector, you see there's the circle next to the lock. And then go ahead and go to the runtime mode.
Look at that. That's awesome. All right. So what are
Yep.
we
So
looking at here,
yeah.
Johnny?
So yeah, and here again, this is kind of the entity representation of the spawner entity. So this isn't one of those entity prefabs, but this is basically the spawner that spawns those prefabs. You'll see that just by default, it's going to give us the transform, the transform components because it had a transform on the base game object. But then down below, you'll see that there's the C spawn data, which again is populated with all those values that we set in the inspector. And then we also do have the C spawner random. And if you kind of do the little value drop down, yep, you'll see that the what the state of that random value is. And one thing that I should point out, kind of why I separated out this spawner random from the spawner data. Essentially, the spawn data, that's all read-only data. We're only reading, how many entities that we want to spawn. What's the position of where we're going to be spawning them. However, that random value, we actually have to write back to that random value because basically every time we generate a random number, that state value is going to change. So basically, whatever seed that we put in, that kind of determines kind of the starting position. And then every time we generate a random value, that state value is going to change just so we can continue updating random values.
Awesome. All right. So now that we've got this entity version of spawner mono happening, this obviously isn't our green sphere, right? Because as I move
Correct.
my square around, you'll notice nothing's happening to the local world, right? So what we need to do in order to generate our green sphere is we need to process this entity using a dots specific version of mono behavior called systems, right, Johnny?
Correct. So it's actually not a mono behavior, but it is a Unity script.
Yeah. Yeah, it's basically what we're familiar with in the traditional game object workflow of mono behaviors, which is object oriented, kind of monolithic. You've got data and logic existing side by side. In dots, it gets split out where you've got that component data that has all of the data, and then you've got these systems, or in this case, an I system that contains all of our logic, right?
Correct. Yeah.
Awesome. Okay, so if we dive into this here, this is our spawn entity system. So this is going to take that entity spawner mono behavior that has been converted to an entity with components on it, and it's going to actually process it. You want to walk us through what it does here?
Correct. Yeah. So, yeah, systems are going to iterate on entities, which typically you're typically going to say, I want to iterate on entities with a particular set of components. So, in this case, this system is going to be iterating across all the entities in the world with the specified spawner components. In this case, we only do have one entity, but we still always want to treat it as if we were iterating across a group of entities.
Hmm.
Um, so yeah, you'll see here, just kind of going up to the top about how we define these systems here. So you'll see that it's a public partial struct. Important that we're using the partial keyword because Unity actually takes advantage of source code generation. So we do need to include the partial keyword there. Yeah, basically Unity does kind of a lot of optimizations on their own to compile this into much more high performant code. So again, yeah, we're just defining these as a public partial struct. You'll see that it implements the iSystem interface. Now, there's two different types of systems that we can use, and we'll be showing you how to define both of these. This one is the iSystem. I'd say the iSystem is preferred to use when you can. This is kind of a newer bit of API, but the advantage of it is everything in there is fully burst compatible. So you'll see basically at the top of the system there, and then above each of the methods, we do have that burst compile attribute. Basically, with the one at the top of the struct, that one's going to define. That one's basically going to tell the compiler, say, hey, we have things in here that can be compiled with the burst compiler, and then each of those attributes above the individual methods, those are going to say, okay, actually go ahead and use the burst compiler to go ahead and compile this method. Now, we're not doing anything particularly crazy in here, so we're not going to get some insane performance advantages for using the burst compiler here. But yeah, the burst compiler, it's kind of a lot of magic. It does a lot of single instruction, multiple data type optimizations to just really improve performance for especially mathematical operations.
Yeah, if we can take a minute, I'm actually going to pull up a picture that really helped me understand it when I was first exploring Burst and what it can do. So this is the Burst user guide. I'll make the link available to you guys. But basically, the easiest way to explain it in terms of what Burst does is it takes your regular C# code, right? And it converts it in two ways. Number one, it converts it into very, very high performant ahead of time compiled assembly. So C# typically is compiled in real time, or what's called just in time, from a intermediary language to whatever language that particular platform you're running on speaks. So if you're on Mac OS, it'll compile out to that. If you're on Windows, it'll compile out to that. But it gets compiled on the fly. Now, there's some pros, some benefits to that. There's also some cons, one of which is performance and efficiency. And so with Burst, what it does is it bypasses that just-in-time compilation, bypasses the garbage collector, and goes straight to assembly. Skips C and C++, right? So those who code in Unreal, you're going to be familiar with that, is the C++ workflow. This skips that and goes straight to assembly, which is what C++ compiles to. So that's step one. Step two is by structuring the data appropriately, you're actually creating alignment in the input and output in the multi-threaded jobs. So we're going to go into jobs here more here in a minute, but anytime you see the word job related to dots, what that is it's a piece of code that can be executed in parallel, in mass, right? So I can have the same block of code executing 1,000 times across 1,000 different threads on 1,000 different pieces of data or entities. And the way it can do that is because of not only what the job system does, but also what the burst compiler does, which is this auto vectorization, which is the SIMD MIMD that Johnny was talking to there. SIMD stands for single instruction, multiple data set. MIMD stands for multiple instruction, multiple data set. And it's an assembly term, and it basically means for a single assembly instruction, which is telling the CPU what to do. Typically, you have a single instruction for a single piece of data to do a single thing, right? That's very typical, that's normal. But with SIMD, you have a single instruction that says, hey, I want you to do this single thing for this chunk of 4 pieces of data, right? Or sometimes it's 8, but usually it's 4, right? And so what that does is it makes it to where every time the CPU comes back around to grab data and start processing, rather than grabbing it 1 at a time, it's grabbing it 4 at a time. And that already right there gives you a performance increase. On top of that, because you've got memory alignment where input and output are right across from each other, theoretically, obviously it's more complicated than that, but we're going to simplify it. You've got the ability to process through these arrays of data as fast as you would do a mem copy, or nearly as fast. A mem copy is literally just copying data from one spot to another. It's the fastest instruction available to us today. So those two things combined, the mem copy level of speed due to data alignment, as well as being able to take advantage of ahead of time compilation and SIMD-MIMD technology, means that this seemingly innocuous thing, this burst compile flag that we're putting on our functions and structures, can actually by itself produce a ×4 or more, I've seen as high as ×10 performance increase, depending upon how you organize your data and how your logic is structured. Right. So it's really easy to pass by that and be like, okay, yeah, that's just a thing I do. But I wanted to stress how, like, when Johnny says magic, it really does feel like magic, because you just toss this little thing on there. And as long as you're abiding by the user guide, which I'll pop this into the chat, it can absolutely blow your mind in terms of the performance increase. Okay.
Yeah,
So
definitely.
going back to
And
that, go ahead,
actually,
Johnny.
while we're still on that point, I do see that somebody in the chat had mentioned, before I've used it, what are some of the potential drawbacks of using the burst compiler? I'd say there aren't. I'd say it's less of drawbacks and more of limitations. So again, kind of like I've mentioned, the burst compiler is only compatible with blittable data types and unmanaged data types. So we can only use simple things. Again, integers, floating point numbers, things of that nature. Again, we can't use many of the regular Unity components that we're familiar with, like game objects, transforms, animators, things of that nature. Yeah, again, all just very simple data types. Although there are a surprising amount of things that we can do with just those simple data types, and yeah, it kind of makes you think outside the box sometimes. So it can be a little bit of a fun challenge. The other thing that I will caution you on is when you have the burst compiler enabled, and we can probably just show how to kind of turn the burst compiler on or off over in Unity. When you have the burst compiler enabled, sometimes you will not be able to see like the full context of some error messages. So, and it usually Unity does a pretty good job about saying, hey, an error happened. This code was compiled using the burst compiler, and there's limited code insights of what's going on. So then, in that case, you might have to go and just turn the burst compiler off, run your code again, and let it and yeah, run again, and then you probably, hopefully, will get some better context about some of your errors there.
Yeah, I would highlight it as the biggest con of DOTS as a whole, when you're leveraging the multi-threaded aspect and the ahead of time compilation straight to assembly aspects. When you've got all of that enabled and you're getting that crazy awesome performance, if there is an error, especially if it's a memory misalignment or some other stack overflow kind of error, one of my favorites is segmentation fault. I've seen that one a few times. It's just a hard crash. There's no detailed explanation as to why. It's just going to crash on you and SOL, right? The good news there is that when you're actively developing in the editor, as Johnny pointed out, you can turn it on and off, right? So as you saw, I just turned it on. I can turn it off by going to Jobs, Burst, and then uncheck this Enable Compilation, right? And that will help, but even still, it's still going to be somewhat difficult to debug due to the multi-threaded nature of the code. So what I mean by that is if you've got a situation where one of your jobs in 1 or 2 instances of it running thousands of times errors out, unless you put in some kind of logging, and logging is difficult for that, it's going to be really challenging to try and figure out what was causing your problem. in the multi-threaded DOTS type of environment. So debugging is definitely harder. With that said, a lot of times what you'll find is that you can test your logic in a more traditional path first. Make sure it's working the way you expect. And then when you go to scale it, that's when you chuck it over to DOTS. And that helps to minimize any chances of problems until, of course, you go more advanced and you start chaining some of these bad boys together. And then you have all kinds of fun. All right. Excellent question. Thank you. Let's see. Let me make sure data between dots and the game object technique, making sure I'm keeping up with the chat here. So yeah, dots in a game object world, getting that data passing back and forth. We're going to cover that in a minute, but I want to go ahead and pick up where we left off here. So we've explained burst compile. The reason for struct, I want to cover that too. The reason why you can't use class, it's along the same lines as to why you have to use splittable types. And that is dots, because it's ahead of time compilation, it can only use pass by value types, cannot be passed by reference. So no pointers, no classes, no managed types of any kind. It needs to be blittable types that can be copied instead of having a reference passed to it. Okay, so that's where you're going to see that struct and all of the basic types being used. Okay, with that said, Johnny, you want to pick us up where we left off?
Yeah. So again, that's kind of the basic structure of kind of how we define the I system and why we do that there. So yeah, again, if we go ahead and define this I system, you see that it's going to force us to implement 3 different lifecycle methods. So there's the on create, on destroy, and on update. You see that these are all just public void functions. And again, I've gone ahead and added the burst compile attribute to each of those, just so everything in there is burst compiled, because there's no real drawbacks to using it in this particular situation here. You'll see that each of the methods takes in a reference to a system state, just called state. That state is going to give us basically access to a lot of things about that particular system. So you see up in the on create, you'll see that I have a state dot require for update, and then I pass in the C spawn data type. What that basically means is that means that the update method is only going to run if an entity with the C spawn data component exists somewhere in the world. So it can be one, it can be more than one, but it has to be at least one. So if we don't have that data component, the system's not going to run. And it's just kind of a way for us to avoid errors. So if there's, if we're trying to run a system against an entity that doesn't exist, of course, we're going to get a bunch of errors for that type of thing. And again, yeah, these are just kind of basic lifecycle functions. So the on create is going to get called at the beginning when we run our application, on destroy at the end. And of course, the on update is going to get called every single frame. Now, the on update is kind of where all the magic is happening here. You'll see that actually the first thing that I'm doing inside the on update is just doing state.enabled equals false. Now, of course, we only just want to spawn our entities one time. So basically what I'm doing is just disabling the system right now. Even though we're disabling it on that first line, it's still going to execute the rest of the update method before actually disabling the system and not running it again. And the reason we're doing it in on update is just so kind of all the setup steps have already taken place first. And then in the on update, that's when we're actually going to go ahead and in the first call to the on update, that's when we're going to go ahead and actually spawn all the entities here. So next up, you'll see that we're using what is known as an entity command buffer. Now, an entity command buffer is a fairly important concept. Basically, what it allows us to do is it allows us to essentially queue up entity operations and then play them back at a later time. Now, one thing to be aware of inside of Unity ECS is any type of structural changes. And a structural change is when we're saying, creating new entities, adding new entities into the world, or we're changing any entities by adding components, removing components, doing any type of operations. These are all going to be structural structural changes. The reason that this is important is because basically the way that Unity ECS stores all these entities in memory is it stores them, in very specific blocks of memory. All the entities of a particular type are all going to be inside the same block of memory. And then when we say to change that, where we say add a component to it, we actually now have to move that data over to another place in memory so it can be with entities of that new like type. So again, they can be kind of expensive. So the best way to kind of go about handling this is queuing up all these operations. And then at one designated point, we can just go ahead and play back all these operations. In this case, I've gone ahead and created my own entity command buffer. To get a little bit more advanced, there are a few built-in entity command buffers where we have, an entity command buffer that say runs at the end of the frame, an entity command buffer that runs at the beginning of the frame. I believe there are a total of 5 or 6 ones that we can actually essentially hook into and schedule work on. But in this case, again, it's just easy for us to just go ahead and kind of queue up all our operations here, and then we can manually play back those operations later on. So you'll see that basically what I'm doing here is just creating this entity command buffer. You'll see that I'm using a temp job allocation, so I can pass this into this job that we're going to be going into in just a moment here. There's different types of allocations you can make for entity command buffers, and going into things like native collections, which I don't think we're using in this example. But there's basically different levels of allocation. So we can do a temp allocation, a temp job allocation, or is it permanent allocation? What am I?
Yeah.
Persistent.
So you got temp job, persistent.
Yeah. And then that basically just you set that based off of how long you're going to need access to that command buffer or that native container.
Yeah. If I could cover that a little bit more, just really quick.
Yeah.
So when it comes to allocations, what it's actually referring to is getting back into that ahead of time compilation that we referred to, right? So because we're now dealing with AOT compilation and not just-in-time compilation, just-in-time compilation has the garbage collector. AOT doesn't, right? So that means we're back into almost like the C++ way of thinking, where we have to allocate and dispose of any of our memory manually, okay? So when we knew an entity command buffer, we're telling the system, I want to create a new bucket of memory in unmanaged space. So garbage collector does not touch it, doesn't even know it exists. And so what Unity did was it put in a safety check system to say, okay, we know you want new memory, but we don't necessarily trust that you're going to take care of this. So we want you to tell us how long you expect to need this memory for. And if you keep it around for longer than what you say you expect it to need, then we're going to flag it and say, hey, this has stuck around longer than you said you needed it for. Right. So to that end, you have these allocator enums. Temp is literally one frame. It's going to live and die in the same frame. Right. Temp job is 3 frames. It's going to live and die within 3 frames. And then persistent is, don't tell me what to do. I'm going to keep this around for as long as I dang please, right? And so it won't give you any warnings at all. That's not entirely true. If you exit out and it's still there, it'll give you warnings. So because we're doing a job, we're required to use temp job. And the reason for this is because jobs have the capability to run across multiple frames. So even if you don't mean it to run across multiple frames, unless you call .complete somewhere in the main thread, it's going to potentially roll over, right? So that temp job there is just to cover your bases on that. Okay, so now if we go back into the spawn entity job, do you want to pick it up there, Johnny?
Yeah, definitely. So yeah, at this point, we can kind of scroll down to the iJob entity, and we can kind of talk about what is going on here. So this is kind of where all the actual stuff is happening. So when we create a job, we basically define some things that we want to happen in our project, and then you'll see that up in the system, that's basically where I'm essentially creating that job and then scheduling that job. And so we can kind of go into what it actually means to schedule a job maybe after I kind of just go over what this iJob entity is. So you see that again, this is another public partial struct. which this is our spawn entity job. And you'll see this implements iJob entity. Now, there are a number of different types of jobs that we can use. Um, iJob entity is an interesting one because basically it iterates across groups of entities. So again, kind of going back to the theory about, we want to basically treat everything as if we're running across a group of entities rather than, just treating, entities one by one and manipulating them one by one. We want to kind of treat it as if we were iterating across a group of them. Again, this is maybe a little bit overkill for this situation because we just have one entity that we're iterating across. But I think it's important to kind of showcase this type of workflow. And again, even though we have just one single entity, it is preferred that we still kind of stick to these main conventions here. So you'll see this public struct, we just have one single field here for our entity command buffer. So again, we're creating our entity command buffer in the system. And then when we create our job, we're passing in our entity command buffer into there. And then, yeah, so you'll see that we just have one single method in here, which is the private void execute. Again, this is all going to be compiled with the burst compiler based off of the burst compile attributes, both on the struct definition as well as the method definition. And then, so you'll see here inside the execute method, we are kind of taking in some of our custom parameters here. Now, this is important because any parameter type that we pass into this execute method, that's essentially going to determine what entities this iJob entity is going to execute across. So basically, this means it's going to look for any entity that has a cspawner random as well as a cspawn data, which again are our two custom data components that we added to our spawner entity. Another thing to point out is you'll see that I have the ref keyword before the cspawner random and the in keyword before the cspawn data. Now, this basically determines kind of essentially our access level to any of these data components. So the ref keyword, that basically means that we have read and write access to our random data component. Again, like I mentioned, the random data component, we actually need to write back to that data component when we generate random values so that the state value can get updated every time that we generate a random value. If we didn't write back to it, then it would essentially generate one random value. And every time we try to generate a new random value, we would just get the same number over and over again, which is not very random. So again, we do need to, again, put the ref keyword before that. It is very important to make sure that we're, defining our access levels to any data component, where if we need, read-only access or read and write access, we need to make sure that we're doing that appropriately. Because when we actually go to, say, schedule these jobs, Unity does kind of a lot of things on the back end where basically when we're actually like scheduling the jobs, basically, I guess, how do I put this? They're kind of like job dependencies, and it knows when we have write access to particular data, and if we have read only access to other particular data, it can kind of schedule things in such a way so that we don't end up in some sort of race conditions where maybe one time we're writing to something before reading from it, or reading something to it in a different order. So it's really important that we're setting the ref and in keywords appropriately. It's always preferred to use the read-only access if you only need read-only access, because that basically means when we schedule multiple jobs that could potentially be running in parallel, that means they can all essentially read from those bits of data because we know that we're not writing to them. So there's kind of like some safety checks that happen on the back end on there. Is there anything that you'd
Yeah.
like to add with that?
Absolutely, yeah. So this is reminiscent. If anybody has had to do multi-threaded code before, if you've had to deal with locking objects or mutexes or any of those situations where you're trying to make sure you don't have a thread writing to a memory space at the same time that something else is reading or writing to that same memory space. That's what the ref and in helps protect you against. It's another one of those safety checks, just like allocator, where Unity is basically going, okay, we're trying to make this as accident proof as possible to where you don't accidentally write in a race condition. So the dot schedule or the dot run in this case, what it's going to do is it's going to actively look at how you've structured your job. And it's going to say, okay, oh, this is reading from all of this stuff and only writing to this thing. Nothing else this frame is writing to this thing. So I'm just going to go ahead and dump all 1,000 instances of this job all at once and just go ham. Versus if I have a situation where this job needs to write to this space and this job needs to write this to this space, the same space, now I need to reconcile which one goes first, right? Another thing that'll happen is if you say, let's say this was an array of values. Let's say random contained an array of floats, and you were using a different kind of job where you were able to index into that array somehow. That's called an iJob parallel 4, by the way. I'll provide documentation on that. So if it's a ref and you try and go out of order, so whatever index you're supposed to be on, let's say you're job number 5, right? And you're iterating across an array of data and you try and access number 6 in your array slot, it's going to throw and it's going to say, no, you can't do that because you asked write permission to this array. If you access slot 6, how do I know you're not changing the info while something else is trying to read from it? Whereas if I say in, where I only want read-only access, then I can jump around all day and it doesn't care, right? Because I'm only reading, I'm not writing. So just some things, read up on concurrency, parallel coding. You'll run into a lot of these same kinds of problems. And the job system part of DOTS, because DOTS is an umbrella term, you've got ECS jobs and burst. Jobs is all about trying to make multi-threaded code less of a headache. And this is part of how they do that.
Yeah, definitely. So yeah, then again, just to kind of reiterate, everything that's happening inside that execute method, that's going to run on each of the entities that again have those components that we pass into there. So if we say had multiple entity spawners, that code would basically run once for each of those entity spawners that we have in the game.
Yep.
So then, yeah, actually going into kind of, what is actually going on inside this execute method, it's actually all pretty straightforward. Basically, we're just doing a simple for loop, going up to the number of entities that we want to spawn, which again, we define in our spawn data. So yeah, again, you'll see that up in the execute, we say, an in on the spawn data, the actual variable is called spawn data. So that's going to give us access to that spawn data component for that particular entity that we're iterating across. So, again, if we were to have, multiple spawners and, one spawner is only spawning 10 entities and one is spawning 10,000 entities, again, the execute method is going to be called for each of them, and they're going to run based off of their individual data that they have associated with them. So again, yeah, if we are doing, spawning 10,000 of these, this for loop is going to run 10,000 times. And basically all that we're doing in here is we're first going to create a new entity using our entity command buffer. So we do an ecb.instantiate, and we basically pass in the prefab that we want. Again, we have that from our spawn data component. Now, this doesn't actually create the entity right there. Again, this just kind of records that to the entity command buffer that says, hey, when we play back our entity command buffer, we're going to want to instantiate a new entity here. So basically, actually, what we get from that new entity is kind of like a deferred entity. So it allows us to kind of do some other operations where we can say, set components on that. Even though that entity doesn't exist yet, we can still use the entity command buffer to, record that we're creating that entity, and then we can, set components on it later on. And then you'll see after that, we're just using the random to generate a new position and a new speed. Basically, the way that we do that is we access our random, and then again, we have that single variable on there called value. So if actually, back inside the data component, you'll remember there is the value, and that's actually the underlying random data there. And then from there, we can generate a random value. In this case, we're generating a random float 3 by using the next float 3 there. And then inside there, we're just passing in our minimum position and maximum spawn position from our spawn data. And then again, very similar thing for generating a random speed, but we're just using the random.value.next float, again, passing in our minimum and maximum speed parameters. And then so after that, we actually have to go ahead and set those data components. So our entity, it already has a local transform on there, which is kind of one of the default transforms that our entity has. That again, it kind of gets from that baking process of just having the regular game object transform on there. So we have access to set that. So we're just going to go ahead and set the position, rotation, and scale on there. Again, just setting the position in new position. Rotation is quaternion.identity. You may notice that that's a lowercase q quaternion. That's because it uses the unity.mathematics version of the quaternion. So, a little bit of a gotcha there, but yeah, just the lowercase q quaternion is the one you want to use for ECS, basically compatible transforms. And then again, we do have the scale stored on our spawn data component there. After that, we're going to go ahead and record operations for adding components. The first one we're going to do is go ahead and add a new speed component. You see that basically the way we do that is we just pass in, the entity that we want to add the component onto, and then we just create a new C speed value. And then we just go ahead and set the value equal to that new speed, which is that random value that we generated above. And then finally, we're going to go ahead and add a component, which is this T follow player. And if you actually go into that, you see that this is a special data component, which is known as a tag data component. So it's basically just a public struct called T follow player, which implements iComponent data. And you'll see that it has no parameters or fields or anything like that in there. So this is basically known as a tag data component. Now, the advantage of these tag data components is that we can say, look for anything that has this tag data component and run some particular operations on it. So it becomes, really efficient when we're, running across groups of entities, and we want to say, hey, these types of entities are special. We're going to, tag them so we can run some specific systems on there. And it doesn't actually add any actual data to the entity. So there's no memory cost of overhead because we don't have any data fields on there.
Yeah, I would like to rewind for just a second here and explain a naming convention that's in use. Due to the nature of dots and how easy it is to confuse different scripts and their purposes as you're going through naming things, a standard that I've adopted that seems to work pretty well and seems to be elsewhere as well is you put a prefix underscore depending upon what kind it is. So C underscore for component data, T underscore for tag, S underscore for system. Feel free to use whatever naming convention you want, but do yourself a favor, save yourself hours of debugging and go ahead and tag it in some way so you know at a glance what it is and you're not searching for things for hours trying to figure out where the heck you put X.
Nice.
All right. I think that just about does it for the spawn entity system.
Yeah, so then we can just real quick go back to just scheduling it real quick, and then that'll basically be it there. So yeah, that's again kind of the system. Again, we're with our entity command buffer, we're only recording operations in there. And then actually, yeah, real quick, I'll just point out. So to actually create the job, we can just do a new spawn entity job. You'll see that I'm setting my entity command buffer to that ECB that I ran there. And yeah, actually, it does allow you to do that if you just take off the .run at the end if you want. So then, yeah, we actually, have that job there. And then from there, we can do, I don't think that returns a job.
You got to
handle,
do
actually.
a schedule for that. That's right. Yep.
Yeah.
Okay. Yep.
So yeah, you'll see that there are multiple ways that we can actually execute this job because again, this job when that code runs, it doesn't actually execute right away. Again, this kind of there's different ways we can go about doing this. So there's run, schedule, and schedule parallel. So what run is going to do, run is just going to execute it immediately on the main thread. Schedule it is going to schedule it for later on in the thread, and then schedule parallel. That's going to um, allow it's going to run later on in the thread, but we can also basically run it in parallel with multiple instances of the same job or other jobs.
Yep. And then the piece that I'm trying to figure out so I can demonstrate it, I'll demonstrate it elsewhere. But there's usually a way that you can grab a handle object from the scheduled job. iJob entity must not qualify. I'll have to dig
Yeah,
a
I
little
think
deeper into
iJob
that.
entity is a little bit different.
Okay. Yeah. So
Yeah, I
with an
think it just
iJob
takes care
parallel
of all the.
4, oops, sorry, go ahead.
I was just gonna say, I think it just takes care of all the automatic dependency handling.
Makes sense. Okay, yeah. So with an iJob Parallel 4, which is another kind of job that is specifically designed, optimized for schedule parallel, you end up with a handle that returns out of it that you can then pass into other jobs to create some very interesting chaining effects where you can chain jobs together. And I've even seen some people go really crazy and spawn new jobs within jobs. I don't recommend doing that as a beginner. Um,
Jobception.
Yeah, exactly. But you can really create these very intricate multi-threaded logic paths that then can execute very complex algorithms, all using every single core that's available on your machine. And then when you're ready to actually complete all of it, like let's say you're back on your main thread and you want to go ahead and make sure that everything has finished across all of that complexity that you spawned off, you can either do handle.complete for a specific parallelized job, or you can say complete all and then pass in a dependency, and it'll make sure that everything is finished before allowing the code to continue. So that's again just a quick demonstration of yet another way that DOTS jobs tries to simplify what is actually a very complex and difficult task of multi-threaded coding.
Indeed. So yeah, in this case, basically when we do a dot run, it's going to execute it immediately on the main thread, which is kind of necessary for how we have this entity command buffer set up, because you'll see that, after we actually run the job, we're going to go ahead and play back all those commands that we recorded inside the job. So if we were to say do a dot schedule on this job, when we try to play back the entity command buffer, our entity command buffer might not even have any commands in it yet at that point, because basically all we're doing is we create this job and we're going to say, hey, run this job later on in the frame, and then when Unity is available to actually execute that job, then it will go ahead and run that. So again, yeah, I'm using a dot run, which is going to run it on the main thread, just right inside the update method there. And then once that's been completed, then we can actually go ahead and play back all the commands that we recorded inside the entity command buffer. You'll see that we do need to pass in the entity manager. The entity manager is another kind of fundamental concept of dots. It's going to allow us to do many things that the entity command buffer does. However, the entity manager is basically just going to execute them immediately on the main thread. So again, we can do structural changes like creating new entities, adding components, removing components, and things of that nature. And again, basically, we just need to use that entity manager to actually play back the commands on the main thread right there. And then finally, at the end, we just need to make sure that we dispose our entity command buffer, because again, we are allocating that in unmanaged memory.
Yep. Yeah. And so the other thing to keep in mind is the reason why we need to call a specific entity manager is because there is a chance that you can actually have multiple worlds running inside of dots. So, for example, you could have a world that's handling all of your rendered entities. You could have another world that's handling maybe a simulation layer of that. You could have another one that's processing all the audio. There's all kinds of different things that you can do. And so, when you do a entity command buffer playback, it doesn't want to assume where you want to play back all of those commands. And so you need to pass it an entity manager. And an entity manager is going to be specific to a given world. In this case, we're using the default world, which every DOTS scene starts with. And so I wouldn't recommend spawning off new worlds at this stage for your beginning stages. But it's important that you at least are aware of its existence. So when you see references to, for example, default game object injection world, that's where that's coming from. That's the default world that DOTS comes with, and you can then create others.
Yeah, good clarification there.
Okay. So I believe that covers the baking workflow. Anything else we need to cover on that, Johnny?
Yeah, no, that again, basically up to that point, all that's going to do is basically just create our entity spawner and then spawn all those entity prefabs into the world.
Yep. All right. So again, just to reiterate, you can take an existing mono behavior game object workflow scene, you can create a sub scene within that scene, and you can use this baking workflow to then go ahead and go ahead and grab a traditional game object, convert it to an entity, and spawn multiples of it. Now, the other thing I want to point out is you can use that same baking workflow. So we're assuming you're going to want to spawn thousands of a given game object, right? Because that's what DOTS is
Yeah,
good at. It's good
have
at
fun.
mass processing. Yeah. However, it's worth pointing out that this same baking workflow, correct me if I'm wrong, Johnny, but this can be used on a onesie twosie basis as well, right? So like if you've got a singular game object that you want to just convert to an entity, you can write the baking to just convert that one instead of doing a whole spawning system.
Well, that's basically what we're doing right here.
Mm-hmm.
We're just basically defining, all the fields for that one single spawner entity.
Yeah. So then with our spawner system, so for example, let's say I wanted to create a plane and I wanted the plane to follow the player, but I only wanted the one plane. I could theoretically just have my plane prefab in the subscene, throw a mono behavior on it that's like a convert plane to entity mono behavior, write a baker on that then adds the corresponding components necessary for it to react to the follow player system. And then that one plane would convert and we'd be good to go, correct?
Yeah, yeah. Again, you can create,
Okay.
as many of these Baker components as you want, and you can, add different components. Of course, you can add tag components if you wanted to, have it um, be affected by different systems. And of course, there's nothing stopping you from using, multiple of these Bakers on a given entity. So, we could create another mono behavior that has another baker associated with that, and we can have both of those on an entity. There's nothing stopping me from doing that.
Good to know. Okay. So the reason why we're showing you the way we're showing you is because we're assuming and encouraging you to think about at scale entities, right? Onesie twosie isn't really going to show you the benefits of dots. You start getting into the thousands, tens of thousands, or hundreds of thousands. Now that's where you're really going to start seeing the benefit. Okay. So that's why we have it structured the way we do, to make sure that you know how to easily spawn out that many entities and you're not stuck doing Control C, Control V a million times trying to get all those entities set up. All right. So from here, just a little bit of rewind going to our basic player controller here. This is for the cube, purely there for the demonstration of moving the box around and having all the spheres follow. I just wanted to make sure you guys were aware that it is in there. It's very basic. You've got your WASD and arrows, as well as your general QE for turning the cube left and right. Feel free to use it or create your own. And now we're going to get into the portion that is a bit more advanced. It gets into the procedural creation of entities from a mono behavior. I would recommend going with Johnny's route just because it is the simpler workflow and it is the workflow that's more encouraged by Unity. However, there are some cases where you need to get a bit more complex. And so I'm going to go ahead and show that off really quick. If I go into, don't save, not that one, this one. So this gets back into the original entity spawner script. Okay. Now this one looks deceptively simple. So what you have here is you've got a material. It's just a basic material. We are using the universal render pipeline, so make sure when you are creating materials, you are pulling shaders from this guy. You can use any of these in here. Those will work fine. If you pull any of these other ones, your mileage may vary. It will probably glitch out or error out or somehow not render properly. If you are looking to write a shader, I would recommend using Shader Graph because you can target URP in there, and that does a lot of the foundational work for you. You don't have to type nearly as much code. Okay, and Shader Graph is available through the package manager. It should already be included, but in case it isn't, again, that is Window Package Manager. And you've got the Unity registry here. You can also drag that down to say in project, or if you have assets that are free on our system, free, you can grab those from the My Assets as well. But in Unity registry, you have this shader graph. If I'm squinting, it's because I'm using a smaller screen that's 1080p instead of my usual 4K. Okay, here we go. Shader graph right here. So yes, it's already included. And so you can actually then create a shader graph URP, any of these guys, right? And that is a visual style creation system. And that'll allow you to create some custom looks and feels if you so desire. But getting back into what we were talking about, we have here a material, and then we are adding in a mesh, not a prefab, but a raw mesh. There's a reason for that. And you can add in as many as you want. This sphere isn't going to show up because it's a Unity primitive, but I can make this literally anything in the project that I want. So we're going to keep it as a sphere for now, and then you've got your entity count. Okay. Now, by the way, question regarding built-in versus URP. You need to use URP or HDRP if you want to use DOTS. DOTS is not compatible with built-in, with a caveat if you want to render anything. If you don't want to render anything, then yeah, you just want to do data processing and then hard sync that to game objects, you can do that. I wouldn't recommend it though, because you're not going to get the same performance at scale that you would get if you went with URP or HDRP. Okay, so getting back into this, if I go ahead and launch it.
And so just to again point out, we're not using any type of subscenes in this type of workflow. It's
yes.
all just kind of regular game objects up to this point, and then we're going to be using just a regular mono behavior to create our entities and spawn them into the entity world.
Yes, and I want to emphasize this is the full manual process. Okay, this is if you're someone like me and you want complete and utter control over every step of this thing. Okay, so
yeah, this doesn't utilize kind of like source generation, like how kind of what I was showing off, where we use like the partial keywords on the I system and the iJob entity. That's going to basically convert it into something that looks similar to what Scott's going to be showing off here.
Yeah. So again, this is full manual. This is a class model behavior. There's no additional classes or anything in here, right? I do have one job that's an iJob parallel 4, right? So that is a struct. I'm going to show you how I use that. But the benefit to this is you're controlling this from the ground up. You have complete control and dominance over how this entity gets created and what is done with it. So there are some uses there. If you're doing procedural geometry, for example, if you're doing procedural creation of things on the fly, this would be the workflow you would need to use for that. Okay. For most people, the baking workflow is not only the easier workflow, but the more advised, the more encouraged. But we're going to go ahead and show this off. So right off the bat, we've got our material, our mesh, and our entity count. The way I do these is a little bit more strict on the permissions. They are private, but if you flag them as serialized field, that then exposes them to the editor inspector without exposing them out to other classes. And then we get into our iJob parallel 4. There's a whole list of these. You've got regular iJob, iJob entity, iJob parallel 4, iJob filter query. There's a bunch of them. The primary ones you guys need to care about is iJob parallel 4 and iJob entity. iJob entity for when you want to process across entity queries. So saying, ref this component in this component, that kind of stuff. iJob parallel 4 for when you just need to do at mass logic execution, not necessarily over a specific entity. Okay. So that's what I'm doing here. What this does is it has a very specific execute function that you need to have in here. That's the execute int index. The index is going to be the job ID, right? So every job is going to instantiate the number of times you need it to be. It's going to go 0 to whatever number of jobs you've spawned, okay? And so iJob Parallel 4, as I mentioned, has that hard restriction of if you're writing to something, you cannot go beyond either direction, higher or lower, whatever your index provided value is. There are ways to force it to allow you to, but by default, it's not going to let you. Okay. A lot of this is going to look familiar. We've got the unsigned integer seed, we've got our entity prototype, and we've got our entity command buffer as a parallel writer. Because unlike before where we were doing .run, this is going to be multi-threaded. We're doing .schedule parallel. So we need that .parallel writer extra on our ECB. Getting into the execute, we're going to go ahead and instantiate an entity based on our entity prototype. Notice I said entity prototype. It's not a game object. I can't put a game object inside of a spawn job because, or an iJob Parallel 4, because that's a managed type, right? So I had to create the initial entity prototype outside of the job first, and then use that entity, which is thread safe, and chuck that into the job to then do my instantiation, okay? So getting into this, I create my instantiation command. I'm then randomizing based on the seed provided. And then I'm setting components. It looks super familiar, right? Very similar to the baking workflow here. Where things drastically change is when we get into the spawn entities function. So on start, I'm going to call spawn entities, pretty normal here. First things first, what world do I want to do all this in? I go world.default game object injection world. That's the default one that DOTS uses for anything game object related. And then once I know what world I want, I'm going to grab the corresponding, whoops, I'm used to Windows. I'm going to grab the corresponding manager for that world, okay? And again, you have to have the entity manager to do any structural changes to a given world's collection of DOTS entities. So then we have our entity command buffer. As you can see, I'm doing the same temp job allocation. And now we get into the fun stuff. Okay, so Unity is constantly changing what components are required to successfully render an entity in DOTS, right? It used to be 2 things you needed. I think now it's 6. And so recognizing that they are still messing with that, they gave us a boon and said, okay, we're going to give you some helper functions to help tame the nonsense a little bit. So to start with, we're going to create this render mesh description. You're going to pass it a shadow casting mode. So do you want the object to cast shadows or not? Do you want it to receive shadows or not? Pretty basic there, right? And then we're going to pair that with a render mesh array. So these are all of our prefab materials and meshes. So our materials and meshes get fed into this. And then we combine those 2 things along with, come on, work with me here, along with this render mesh utility dot add components. So this is a helper function that's then going to basically query Unity and say, okay, what nonsense do I need to add here to get this working right? And it's going to automatically go ahead and add all of that based on the prototype that you feed it, the manager that you feed it, the render description that you feed it, as well as the render mesh array that you feed it. All right, so all that just to draw something. Now, the advantage here is I have complete control on this, right? I can come in here and I can say, oh, I don't want this to cast shadows. I do want it to receive shadows, right? I can have control over what material it uses, the mesh it uses. I can build out an entire tree of hierarchical objects to create a complex procedural mesh, all without having to touch the inspector, right? So pretty awesome stuff there. Okay, so we go into our for loop. We're creating all of our prototype entities. We're manually building out all the components on those entities. And then we're taking that prototype, creating a job, scheduling the job, different from .run, right? We need to feed it a total count. So that's the 0 to whatever on the index. And what that means is it's going to spawn that number of times of that job, toss it out to the threads to do the work. You get control over what that batch count is. Am I doing 1 job per thread every time the CPU comes around and says, hey, I'm ready for work? Or am I doing 10? Am I doing 20? In this case, we're doing 128 because it's a relatively small load job. The bigger the load of the job, the lower you usually want this number. but your mileage may vary. You can experiment with it and adjust it as you see fit. So because I'm scheduling it, I then need to call .complete. And then .complete is me telling the system, the job system, that I want the main thread code to completely halt until all the jobs finish. This is critical if you plan on doing something with the data immediately after. Now, in this case, I'm not. I'm just putting this in here to demonstrate how you would schedule and then finish a job. Ideally, you want the distance between your schedule and your complete call to be as far as possible, right? Because you're going to give the CPU time to execute that job before you call complete. And here's the catchy part, or tricky part, I mean, that schedule doesn't guarantee that that's when it kicks off. You're just scheduling it to kick off, right? So your CPU might instantly kick off those jobs if it has available threads. If it's bogged down with other stuff that it needs to finish, then it's just going to stick it in the queue and say, okay, I'll get to you when I get to you. But .complete is your way of saying, okay, I don't care what position in line I am. I'm not going a step further until I know this job is finished. Okay. After all the jobs are finished, we push through our playback and again, go back to that whole disposing of the memory that we've allocated. For those of you who want to play around with native memory more, there is a unity.collections namespace. And inside of here, you have native arrays and native slices. Just to quickly break down what those are. Native arrays can be an array of any blittable type, floats, ints, float threes, any of that fun stuff. And that is unmanaged memory. It is extremely fast and performant for use in jobs, right? You'll notice in jobs, if you try and do something like this and pass that in, it doesn't like it. But if I do something like that, you're good to go. It likes it. Doesn't have a single problem with it. And the best part is if I had some extra symbols in there. Best part is if I have a array assigned, and this is going to require an allocator. Come on.
Gave you the wrong, yeah.
There we go.
Happens all the time.
Right, so I can do something like that. And then let's say I wanted to hit different positions in that array. Let's say I wanted to get tricky, right? So I'm going to create what's called a native slice. What a native slice allows me to do is I can come in here and I can say new slice, and I'm going to base it off of my float array. And then you'll notice I get to specify a start and a length, right? So why would I care about this? Well, because if I've got an array of 1,000 floats and I want my job to iterate only over 100, rather than copying over the entire 1,000 floats, I can use a native slice to only work with the 100. My job just became significantly faster. What's more, it resets your index to where 0 is now wherever you say start is, right? So you can get really clever there. And native slices, at least as far as I can tell, Johnny, correct me if I'm wrong here, native slices are basically pointers. They don't seem to have a cost allocation to them. Like you don't have to call dispose on them. So you can allocate them all day. And as long as what you're pointing to doesn't get disposed, the native slice remains valid. So that's pretty handy there as well. But again, native arrays, it is unmanaged memory. So you do have to call dispose when you're done. Allocations and disposing are expensive. So typically you want to do your allocations up front and your disposes at the end and try and minimize how often you do it per frame. No different than garbage collector calls. Last but not least, once we're done spawning all of our procedurally generated entities, we are calling our destroy entity using that entity manager that we referenced earlier to clean up our prototypes. Why? Because otherwise we just have prototypes just dangling, not moving, not doing anything, and we don't want that. Whew. Okay, that was that. As you saw, this is all done in a single mono behavior using regular mono behavior code for the most part, with the one exception being this iJob parallel for job, right? This is just as fast as the other, but the other one doesn't require all of this nonsense, right? You can just use a prefab, call it a day. You don't have to procedurally add literally everything because this is building an entity up from scratch, okay? Cool. Moving on from here, we should probably talk about the big kahuna, the most important piece in all of this.
We're actually running systems across a large number of entities here.
Yes. So now let's talk about this bad boy. So this is the most important script in the whole thing. What this is showing you is how to take all those entities that exist in the world that we've made, that we've gone through all this effort to make, and actually do something with it, right? So we're going to start off. You'll notice here, this is inheriting from system base. You also have iSystem. You use iSystem for strictly DOTS compliant execution. System base gives you the ability to bridge to mono behavior or non-DOTS data, but you have to do it very carefully. There's a specific way to do it. Is that about right, Johnny?
Yeah, that's fair.
Cool. So for example, if this was an iSystem, I could not do this, right? Because game object is a managed type, iSystem's going to go, I don't want that. That completely breaks burst, and so it won't work. Okay. So again, iSystem for pure dots logic, system base when you need to pull data from a non-dots thing. An alternative that I could do as opposed to doing this game object reference and storing the cache here, this is pretty messy, honestly. Probably not the best way to be doing this, right? What I'm doing here is I'm saying, okay, when I start this frame, is main player null? Yeah, if yes, find the player and then go ahead and grab its position every single frame. Not the most performant thing in the world, right? Alternatively, I could assign a script to the player that updates a static variable called player position. And because it's static, it's thread safe, it's a float3 blittable type. Now I can use an iSystem. It's DOTS compliant. I don't have to mess with the system base at all. Okay. But because I'm doing it this way of fetching the game object and pulling its position from the game object, I have to use a system base. So you'll notice there's no burst compile anywhere on here. Okay.
Correct.
I do have this require for update C_speed that borrows from iSystem. It's a very handy trick that Johnny actually pointed out to me. And what this does is it simply makes sure that until there's at least one entity that has C speed on it, on update just doesn't run. Doesn't need to, right? Okay, so answering a question that came back from before, the way you get entities to follow the player, which we showed off in the in the cart demo, micro cart demo, is you grab the data, you have to store it to a blittable type, okay? And then you can pass that blittable type into your either iJob entity, or you'll see this big giant note here, and what's called an entity.forEach. Okay. Either one works. I'm going to let Johnny explain the pro con here in a minute. There's just two different methods to do it. Okay. So with the iJob entity, it looks like this. Entities.forEach looks like this. So Johnny, you want to go ahead and explain what we're looking at here?
Yeah. And actually, before we get too far into the weeds on this, just going back up to the top of where we're defining this system base, it's also important to point out that we're doing a public partial class rather than a struct. So a system base is a class. So it is it's basically a managed system, is what you might see some APIs reference this as. So yeah, and then going down again, we're doing something very similar to before, where we're just getting or we're creating this basic move job, and then we're gonna create this. So we basically get some data that we're going to need. So in this case, we need, of course, the player's position. Again, we're just getting that off of the regular game object, the main player.transform.position. And then for our delta time, you'll see that we do something a little bit different than how we would get delta time in a regular Unity application, where we're using this system API. The system API is definitely a very handy thing. It's kind of a recent addition, but it allows us to do a lot of cool things. Like we can say get data from other entities using it. One particular thing that it allows us to do is it allows us to basically access the time component. So if we need to say get the elapsed time in the world or the delta time for the particular frame, this is how we would do that. So we're just storing that into a local variable there. And then, yeah, we're going to be passing those into the basic move job, which is what we'll be getting into now. So again, this basic move job, this is going to be another iJob entity type. You see here that we're defining this with two public fields here. Again, one for the player position, one for the delta time. And then, yeah, going into the execute, you'll see that this is going to run across everything with the local transform, which again is kind of one of the kind of the ECS version of the transform component. And then, of course, we're going to be writing or reading to and writing from, or I had that backwards, reading from and writing to that transforms, just so we can kind of, update its position each frame there. And then the other thing that we have is the in C speed. And again, we're just going to be reading, from the speed component, so we can determine, how much we need to move our particular entity by any given frame. So you see, first thing that we're going to do inside here is just get a reference to the current position, just by doing a transform.position. And then I'm just going to do a quick check on there to see if we're close enough to the player position. So if we are, within 1.5 units from there, we can just go ahead and return out of there. Again, this execute method is going to be running across every single entity. So, if there's, one entity that is, within that 1.5 unit range, it's going to stop. But if there's any other entities that are much further out, they're going to continue to update. So you'll see that first thing that we're doing is just getting a target direction. You'll see that I'm using the lowercase m math.normalize. Again, that's kind of the unity.mathematics. We have a lot of nice helper functions on there. So of course, we're just going to go ahead and normalize the player position minus current position, which basically gets us the direction from the current position to the player's position. And then basically we can go ahead and multiply that by our speed, and then multiply that by delta time. And then that basically, and then add that to our current position, which gives us the new position that we want to go to. And then we can just assign that new position back to the transform.position. And then, yep, another good thing to point out is you'll see that, again, because we had that tag, that T follow player that's going to be on all those entities that we're spawning, we do also include the with all attribute above this basic move job. So that basically means that we need three components for this job to affect any given entity. So it needs the local transform, the C speed, as well as the T follow player. It just basically needs those at a minimum. It can, of course, have many more components, but those are the three that are required for this job to execute on those entities.
Yep. So as you can see, we can just use that same iJob entity system that we used in the spawning system to go ahead and move entities around. The one con to this, I would actually recommend doing it this way if you can. The one con to this is regarding debugging. And there may be an API that I'm not familiar with that fixes this, but the problem that I've found with this path is when you're trying to trace where a problem is occurring in your jobs, this doesn't let you assign a name to the job that assigns from this. You would assume that Unity would name it basic move job, right? Well, unfortunately, no. What it does is it says, this is going to be S basic move system dot job, and let's just enter in a bunch of random numbers, right? And so there's no real way to, if you get a throw, if you get an error and it says, okay, yeah, no, this job is failing. If there's only one job in the system, then okay, no big deal. But let's say you had 6 or 7, it could get very tedious trying to figure out which one of those jobs is airing out. So in that instance, you might benefit from doing an entities.forEach. So what entities.forEach allows you to do right off the bat is this dot with name, where you can provide a custom name of your choosing that will actually show up as that name in the system window, as well as in any logs that spawn off. It doesn't have any effect on the runtime, though, so keep that in mind. If you deploy a runtime and you get a crash report, you're going to still see the job gibberish number. It's not going to keep the name. It's strictly an editor-only benefit. But you can see the same dot with all here, right? So I have to actually do a dot function call for that, whereas this is an attribute. And then I do a dot for each. This dot for each is the same as this execute. I then have to create a lambda function because this dot for each function call takes a function as a parameter. So the lambda has to have parameters. So I'm going to do my ref for my transform and my in for my C speed. I then do that lovely arrow lambda, that telltale symbology, execute my logic. And then at the bottom, I say schedule parallel. No real difference here, right? Now, another big thing is if I pass in, I think it'll let me do it here too. Correct me if I'm wrong, Johnny, but I should be able to do that. And then I can say var handle equals, I believe. Yes, yeah. Awesome. Okay, so this allows me to say handle dot complete, but more importantly, it also allows me to, let's say I have another basic move job. So like, let me just like clone this and call it something else, handle 2, right? So I can feed handle into here, right? And then now what's going to happen is this will not execute until this finishes. But something interesting happens. It doesn't require all of them to finish. It only requires the same index to finish, or at least that's what I've been seeing. They might have changed it with the latest one. I haven't tested it yet in V1, but in V.5, that's what I was seeing, where if I have 2 jobs that are chained together like this, and index 5 of job 1 finishes, then index 5 of job 2 will kick off in the next batch round. And so that's where you can start to have some really interesting chaining occurring. But be careful with that, because that also means that you need to make sure that whatever you're doing in here doesn't rely on more than the same index value of the data previously. If it does, then you're better off doing a dot complete and then initializing the next set of jobs. Okay.
Yeah, and I will point out, if the dependency handle stuff starts to get a little bit confusing, if you do not define, or if you don't like pass in any type of dependency and you don't, return a dependency, basically that job is now going to be associated with the automatic dependency management of Unity, basically just associated with the system. So that's again typically the easiest way to go about things, is just having Unity, worry about all the dependency management.
Yep. All right. So to wrap things up here, I do see the question just now. I'm going to get to it in just a minute, but I want to go ahead and wrap on the template side. So we've shown off the 3D side. Let me go ahead and get back into the scene here. All right. So we've got our, hopefully I didn't break something with all of my fun. Come on. There we go. All right, so we should see all these green spheres descending from the air. There we go. They're chasing me, right? So we can see how that integrates. So now we're going to show how that works with 2D. Now you would suspect that 2D is different from 3D, given how we're having to do all of this custom conversion work and everything like that. But if you're doing procedural, it absolutely does. But if you're doing the baking system, it's actually more or less the same. And so if I go into this template, this is the micro platformer template that you have. I can go into scenes in here. Here's the primary scene. I have a feeling a lot of people are going to like this template. Very reminiscent of Super Mario Brothers. Got your animations, right? Pretty cool. And now I can go into my dots primer variant. We're using the baking system here. And so if I load this up, just to show you what is in here, Entity Spawner, I've got this alien variant as my prefab. It's a 2D sprite system, sprite renderer, right?
Nice.
Cute little alien, all right? And then so if I go back to my scene and I press play, I've now got a bunch of aliens chasing me. Right? Now they don't actually do anything because I don't have collision on, right? And there's a reason for that. I would recommend trying to do some of your own simple physics checks before doing the actual DOTS physics stuff. It's still relatively experimental and can be very complicated. At least per the last time I messed with it. Johnny, you might have some different experience. But if you're wanting it, you can download it. So it's going to be Unity 3D DOTS physics. This guy right here. Right, so it is in preview. The way you add it, and this goes for any of the other preview packages. You go to Package Manager, Window Package Manager, right? The plus sign. You're going to add package by name, and you'll put com.unity. What was the full?
Physics.
Yeah, .physics. Oh, it went away on me. Lovely. com.unity.physics, and then you put the version number in there that you want. So that would be the 1.0.0-pre.15, and you would just press enter, and that would go ahead and add it for you. Keep in mind, it's still a little rough around the edges. There are samples that you can grab. So Unity 3D DOTS physics samples right here. I'll provide this link as well. So you can get into the physics samples here, and it provides you with all the basics right here, right? So if you're feeling ambitious, feel free to mess with it. Otherwise, by default, you're going to have to do your own simplistic collision detection if you want to have the entities react as a result of interfacing with a game object or each other for that matter.
Yeah.
Okay.
And yeah, I think you might be surprised about, how much performance you can still get even just with basic distance checks across, tens of thousands of entities. Because again, with the burst compiler, and especially if you're scheduling these across multiple threads, it ends up actually being, just quite efficient. So.
Yep, absolutely. Okay, so regarding the question, Josh, you hit it on the nose. iSystem versus system base. iSystem, correct me if I'm wrong, Johnny, but because you're able to burst compile the entire thing, iSystem generally is seen as faster, correct?
Yeah, so like the code running inside an iSystem, it can be faster if you have it burst compiled, as opposed to a system base. However, that doesn't actually change any of the performance against any jobs that you're scheduling. So you can schedule burst compatible jobs from both iSystem and system base, and those systems are both going to run equally the same.
There you go. All right, so that covers both the 3D and 2D templates. That covers every single script that we added to those templates. There are still plenty of scripts in there provided by the standard Unity sample projects, so feel free to use those too. And again, just to recap, anything free, anything open source, fair game. If it's paid, please, let's just try and keep it fair. Let's stick to the freebies, okay? All right, Johnny and I will be around off and on. We'll be monitoring the Discord forum. We'll be able to answer any questions you guys have as best as we can. And other than that, if there's not any other questions, which doesn't look like it, I'll give the chat a few seconds. 1, 2. Okay. So with that, everybody, thank you so much for joining us for this kickoff. I'm going to go ahead and close this down, and we'll be around in Discord. And yes, awesome. The recording will be available for everybody. You'll be able to jump back in and rewatch it at your leisure.
Great. Have fun, everybody.
All right. Good luck.